Welcome to, what are we going to talk about? Let's talk about Android development today. I'm Chet Haas. I'm on the Android UI Toolkit team.
And I'm Romain Guy. I work on the Android team. I'm working on new graphics and layout stuff that hasn't been announced.
How incredibly vague.
That's right.
So today we're going to talk specifically about the naughty bits. I called it that because I liked it.
Because you have no idea.
I had no idea at the time. Like, I don't know what we're going to talk about, but you know what? I like that title right there. So we're going to keep that title, and we're going to make it mean today, basically talking about a series of articles that came out on Medium.com that was a collaboration of basically a lot of people on the platform team at Android, where we tried to do a brain dump of all the patterns and anti-patterns that we'd seen over the years, app developers sort of taking assumptions that they had about other platforms that they worked on or other implementations using the Java programming language and doing things that are essentially wrong to do on Android and ended up with bad results. So we put all this information into an incredibly long internal document, and then we split it up into 10 very long documents and put them up on Medium.com. So I would encourage everybody to check those out. I put up my name there just for self-gratification, but also because you can then find it. So please check those out. But specifically, today's talk is around some of the information in those articles. About 4 months ago, we were doing some user group and said, oh, why don't we do a talk around this thing? We have about an hour. Let's put all the information from 9,200 pages worth of information into this talk. And we went there, we gave the talk, and we got about a third of the way through, and an hour and a half was gone. So we're not going to talk about that. We've already talked about that. Let's talk about some other stuff that we haven't talked about yet.
And actually, how many of you have read those articles already? Just out of curiosity. Wow.
Okay, the rest of you,
you can stay.
Go read them now, and we will wait. Are they done?
I think so.
Okay. Good job, everyone. Now let's repeat all that information in presentation form. So, why is mobile so difficult? So we want to talk about some of the sort of higher level ideas. I would say if you read nothing else from that set of articles, then I would be very unhappy. But point two is, I would say if you read nothing else except the first one of those, which is called Understanding the Mobile Context, that's sort of the bigger ideas of not just what the rules are, but why they actually matter. What's the context of developing on mobile that makes it so very difficult and makes these rules so very important to get a well-performing and nice user experience application for your users. So let's talk about some of those things. So memory, turns out it's limited. It's very limited. So the phones that you have in your pockets are probably, I don't know.
2 or 3 gigs of RAM?
Yeah, 2 to 3. Is 3 coming now? Okay.
Yes.
4 maybe, possibly as low as 1 in a lot of the world. It's 512 megs is actually quite common. And it's not just common on the older phones, it's also common on newer phones that are being sold into cheaper markets. Right? There's a weird thing about Moore's law where you assume that everything's going to get faster and better, and in general it does, right? Moore's law, does mean that it's cheaper to make these things, but it doesn't mean that the other things go away. Those same phones are still in people's pockets out there being used every day. Moreover, it means that the low ends, today's sort of reasonable mid-range phone is possibly going to be the low-range phone for a long time to come. So don't assume that just because you got a good deal on a phone that has a reasonable amount of memory, that all of your users have the same good deal in their location.
And something else that a lot of developers do, we tend to compare the specifications of our phones to computers that we know and use every day. So I see a lot of people who say, like, I have 3 gigabytes of RAM on my phone, it's almost as much as my laptop, I have 4 gigabytes on my laptop. But it turns out that some of our phones today, they have as many or even more pixels than a lot of computers out there. I mean, even this morning I was working at my workstation at Google. I have a Mac Pro, like a really beefy machine with 64 gigs of RAM, and my 30-inch display has just as many pixels on screen as my phone that sits in my pocket. And I actually looked at the activity monitor on my Mac, and my Mac Pro was using 20 gigabytes of RAM to drive the same display as my phone does. So we don't have 20 gigabytes of RAM just yet on Android. We'll get there someday. But be very careful when you make those comparisons, and it's something we're going to get back to, like with CPUs and GPUs and storage. The numbers feel familiar, but they don't mean the same thing as they do on desktop and laptops.
Another dynamic that's important about memory on Android is everybody is sharing this limited pool. Right? So if you are taking up a lot of space for your activity when it launches, the system may have to go around and kill other things to make it possible for your activity to run. And then when you go in the background and the user goes back to the launcher, that may take a while because maybe the launcher had to be killed in order to allow your activity to run. And then your activity may also be killed when there's other activities looking for memory, because if you're taking up a lot of memory, you're going to look really juicy to the task manager when it needs more memory to run.
And that's very important, because I know that your application is the most important application. It is to you. You know, my applications are my most important applications. But I've seen applications that basically try to game the system, and when they're in the background, they try to refresh their caches, or they do everything they can to stay around in memory so that when the user gets back to the application, they won't suffer through a cold startup, so the app is still there. But what they do in the process is they kill all the other apps on the phone, so they make everybody else look bad. So you have to work with each other. We really want the whole experience on the system to be good. It's not just about your apps, it's not just about the standard apps on Android, it's about the whole experience throughout the day.
Let's talk about CPU. It turns out that it's slower than the CPUs you're used to on desktop and server. Much, much, much slower. And another dynamic that people don't necessarily realize is it's quite often throttled. So in order to get the maximum battery time that we can out of these devices, we end up running things as slowly as we possibly can for as long as we can. So we have clever things on the system like doze mode that hopefully you heard about earlier today that allows us to just slow down the entire system and not do much when the system is not being used. But even when things are being actively used, the user is staring at the screen, reading information, the CPU is probably not at its highest operating mode because we detect that there's no user interaction, there's nothing running that may require that thing. But that means in general that some of the things that you may expect out of a CPU with even the speed that it has on common mobile devices may not be true in all situations. That you're not going to get the performance that you thought you would have in these common situations.
And actually, recently got a very interesting question by email. Someone was asking me, was telling me that his whatever algorithm he was running slower than he was expecting. So I was telling him that it's probably throttling because the device was not busy enough. So the CPU was running probably at 300, 600, 900 megahertz, something pretty low. And then he came back to me saying, but it's funny, when I shake my phone, then my algorithm runs faster. And it's true. When you shake your phone, you're probably waking up a bunch of sensors, which are in turn waking up a bunch of processes. So we bump up the frequency of the CPU, and your app goes faster. So you could try that if you want to send your email faster, whatever. Shake your phone. Not recommended to do it all day. But the reason why we throttle, Chad says it's battery life, but it's also thermal issues. The latest batch of CPUs that we have, there are multiple cores. And the truth is, if we were to turn on all the cores at the same time, at the maximum frequency, your device will probably melt, or hopefully reboot before it would melt. But there's so much energy that your phone can dissipate that we cannot run the device at its full speed. And be also very careful with the numbers that you get by looking at the back of the box when you buy your phone. So you see it's a 2 gigahertz CPU. It is not, because most of the time we're going to run throttled. And you're going to see it has 8 cores. It doesn't. It has 4 little cores and 4 big cores, and we're going to use some of them at some point and some of them at another point. We're not going to use all of them at the same time. The best way to know what's going on is to use systrace. We covered that tool extensively at various conferences, and you can probably find the talks on YouTube. But systrace will show you how many cores are active and at what speed they're running, and you might be really surprised by what's going on.
I like the idea of shaking. Maybe if you just play the vibrate thing like constantly, then that would provide enough shaking to wake the phone up. It's just techniques, just performance techniques. All right, let's talk about GPU.
That doesn't mean you should run the vibrator in your application when you want it to go faster. Don't give them ideas, they're going to do it.
Maybe I should hold up my hand. I'm not being serious now. Okay, see the previous slide. So all the stuff that we said about CPUs certainly applies to the processor for the GPU as well. There's some other things that are specific to the graphics side. For one thing, texture uploads are very expensive. A lot of things trigger texture uploads, may or may not be obvious whenever we're drawing a path, whenever we're entering new characters of text. This is the first time we've seen them, we're going to draw them into a bitmap that's going to get uploaded as a texture. Whenever we're doing vector drawables or other things that end up being software rendered into paths, those are all texture uploads, in addition to the obvious stuff of bitmaps. So those are expensive, as are General fill rate operations.
Well, it's just related to the bandwidth. So just like texture uploads, we have a lot of pixels on our devices, and we need a lot of bandwidth to be able to feed the display. And usually to draw those pixels, we need to use intermediate buffers and all that stuff. And the bandwidth on mobile has not been growing at the same speed as the rest of the system, so the CPU, the GPU, or even the screen density. So it's still very much a problem today. And we, again, covered that extensively in previous talks where we mentioned things like overdraw and blending and why you should avoid them. GPUs on mobile have other issues. I mean, they're really good, they're incredible, given they are run on phones, but you can't really compare them to desktop GPUs or your laptops or even your consoles. I mean, just to give you an idea, like a fairly power-efficient GPU on a desktop uses about 175 watts of power. On a phone, if we can dissipate 4 watts of power, it's really good. So, we can do what they can do. And even if you conserve the bandwidth, even if you're really careful with your textures, our GPUs are still very limited in terms of how many computations they can do on every pixel. So you probably don't care if you're not writing OpenGL code, for instance, but if you're writing a game or OpenGL on your application, something you need to be very careful about, especially on older devices. No matter what, don't test only on recent devices when it comes to GPUs. There's a huge gap between the Nexus 6P and devices from 2 or 3 years ago.
There's also an interesting dynamic that comes up when you're looking at, as we said, fill rate that's not necessarily keeping up with the curve of everything else, and these devices that are coming out with amazing density. What was is it the Nexus
4K?
6 or the 6P is like 550 DPI, just huge numbers, which is really awesome for screen resolution, but if you imagine that's how many pixels we have to actually fill on every single frame, then that's kind of problematic if you don't have the bandwidth to actually do that appropriately, which is why we have a lot of these recommendations around it.
But the good news is that we thought we were pretty much done with density because we have so many pixels these days, but VR just arrived, and for VR you need even more pixels, so it's going to get even worse.
Fortunately, people only have 2 eyes, so it can only go so far. Memory. So in general, a lot of the tips that we have about performance boil down to tips about memory, because on Android and the runtimes we're talking about, memory is so closely tied to performance. There's a lot of dynamics around that. Let's talk about some of those. So when you require more and more memory, you're basically allocating a larger and larger heap. It takes more processing power to actually allocate that heap to increment the size over time. It also means that there's going to be task thrashing. We were talking about this before. If you take a lot of memory, someone else has to die to ensure that you can live, and vice versa when you go in the background. Allocations are going to take longer because there's simply more information to wade through for the garbage collector to actually figure out where to put that thing, where the free space is. Collections are slower for the same exact reason. And there's just general more activity for the garbage collector to run through, allocating, collecting, doing hopefully not, but probably full GCs to actually get memory back in the system. So we thought it would be useful to sort of walk through some of the ideas around garbage allocation and collection in general, so you can understand the context of why this stuff costs so very much.
So this is how a garbage collector works.
Okay, any questions? Okay, so if we go into the technical description, the squigglies on the left indicates, I don't really know. I still have a slide from somebody.
I'm disturbed by the squigglies.
Somebody in the squiggly dimension is trying to allocate something, and they come up with a blue rectangle. I don't know why it's blue, I don't know why it's a rectangle, but they want to allocate space for it. So it looks at the garbage, at the heap, and it says, okay, I want to allocate this thing. We put it in there, then we enumerate all the things that have references in the enumeration phase. The mark phase says, okay, what are the things that don't have references, because those are the things that we can get rid of, and then we collect that, right? So we free up that little red thing in the middle, we freed up the space for that. That is now space that can be used for a future allocation in the heap. It's important to note that on Dalvik, there's 2 different pauses that happen during this process. There's a pause during enumeration where we actually walk the heap and see where the references are to all these objects. And then there's the mark phase that also has a pause. Part of the mark phase is okay. It can do that concurrently with other threads, but part of it needs to pause everything else in the system at the end of that mark phase to basically do a post-process and say, okay, are there any changes since I ran through the first time?
And it's important to remember that a pause pauses all your threads in your application. So it's not just the UI thread. It's going to be paused. You're going to pause your background threads. That also means that a background thread doing too much GC activity will impact your UI threads, so your animations, your layouts.
And you can see these in the log. These are not GC for alloc, it's other GC operations, concurrent GCs. There's lots of information about GCs in the log. You can see some of these things coming out, and if you wonder why they're there, this is why. So on ART, there were improvements, huge improvements made to garbage collection allocation in general. One of the big improvements was there's no longer a pause during the enumeration phase, and there's a smaller pause during mark, but it is still a stop the world pause. So at the end of the mark phase, they're going to do a quick pause just to sort of collect the information and move on from there. So now let's look at a more problematic situation. This is the GC for alloc situation. You come in, someone wants, yet again, a blue rectangle allocated, and it comes in and it says, okay, well, I've got a space for that. How about a second blue rectangle, because I had such a good time allocating for the first one. And it walks through the entire heap, and it cannot find a contiguous block of space large enough for the second blue rectangle, so it needs to free up space for that. Then it does a GC for alloc, and there's a huge pause, right? So this is the really problematic thing about GC, not just that it's a huge pause, but it basically happens at exactly the time you do not want it to. You may be in your inner loop and you're doing something that triggers an allocation, that triggers the need to actually walk the entire heap and free everything possible just to get memory to allocate that thing. Nothing can continue in your program until that is freed up for you so that it can be put on the heap. So you're basically going to pause right in the middle of an animation or rendering or whatever, something on the UI thread.
And it is important to know that GC for alloc does not make any guarantee that you will be able to actually allocate what you want to allocate, because if the heap is fragmented, and we'll get back to that because there's been changes with ART, but when the heap is fragmented, there might not be a single slot available that's big enough to fit your object, in which case you will get a crash, an out-of-memory exception. And the interesting part is you could have, dozens of megabytes of free space in your heap, but because of fragmentation, a tiny allocation could fail and crash your application just because we need contiguous memory in the heap. It's actually fairly easy to do. You can try for yourself. If you have a Dalvik device, you can allocate a bunch of objects in a list, and then you null every other object in the list. You wait for a GC. So you will have fragmented the heap, try to allocate another big object, and you will run out of memory, even though you have a ton of memory available. And that happens a lot with bitmaps, which is why in ART, they've introduced the concept of the large heap. So it's a special heap for large objects, and bitmaps in particular are a good candidate for that. So not only does it help with the heap fragmentation, because we know that we're likely to find large contiguous space in the large heap, but it will also make every allocation and garbage collection in the common heap faster, because there will be less memory to look at.
Another dynamic we've seen a lot is the prevalence of low-end devices in the world. In general, we referenced this before in the context of memory, but basically the device in your pocket, guaranteed it's faster than most of your users, and it has more memory. So we're talking about Moore's Law. It doesn't always apply, or at least it doesn't apply in the way you expect. So those low-end devices are going to be in the world for a long time to come. So your application needs to deal with them unless you simply don't like those users. Smooth frame rate. So this is an important one. We talk about 16 milliseconds a lot. I guess it's a number that we like a lot. Basically, you have 60 frames a second. That boils down to 16.67. Milliseconds that you have to do everything, right? So you need to process your input, you need to process your animations for that frame, you need to do any measure and layout that hopefully didn't happen in an animation, but sometimes it does, and process all the drawing commands for the things that changed, and then those get sent over to the render thread. All of that stuff goes through. Everything has to happen in 16 milliseconds in addition to anything else that was going on in the system that may cause a pause there. Right? So 16 milliseconds, if it doesn't happen by then you just missed a frame, and you just missed the opportunity for smooth frame rate for your users. Another element of frame rate that's not as obvious is that consistency is good. I would say in general, it's better to hit 30 frames a second consistently than it is to hit 60 frames a second most of the time, and then occasionally you're going to pop out. Like if you know you're going to pop out and there's nothing you can do about it, then go back to the drawing board and do something about it anyway. But it would be better to sort of back off to a slower frame rate, at least one that you could deliver consistently. Otherwise, what the user is going to see is smooth, 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 pause, skip. Right? It's very noticeable when you're going to drop frame rate just occasionally. It's a noticeable blip on the screen.
That's actually something that, for those of you who play games, it's something fairly common in video games, especially on consoles, where the video game developers would rather target 30 frames per second than have a fluctuating frame rate, which can be very distracting when you need to play animations or have like reflexes in a multiplayer game. And the thing is, on Android, because we are vsynced, and there are different types of vsync, but Android has always been vsynced, at least at the compositor level. When you miss a frame, it's not like we're going to drop to 59 frames per second or 58. You're going to go all the way down to 30. So if you miss every other frame, you're going to go 60 frames, 30 frames, 60 frames. And it's extremely jarring for the user. So like Chet said, if you cannot hit 60, you should maybe hit for 30 consistently instead.
Or pop up a dialogue and tell them to shake their phone.
Or have a setting.
Let's talk about runtime. So Dalvik versus Art. We talked about some of the differences in the collectors before. There's a really important dynamic about whether they can defragment the heap. So this was sort of implied before, but Dalvik basically, once you allocate a thing, if it's going to stay there, it's going to stay at exactly the same place in the heap. There's no point at which Dalvik can actually move things around. So if you allocate a bunch of stuff and then other stuff goes away, the stuff that's still allocated and referenced somewhere is not going to move, which means it can fragment over time, and eventually you can run out of room to allocate other items, not because you don't have the space in the heap, but because you don't have the contiguous space. Art made a change where it can actually defragment that heap when the app goes into the background, and there's an appropriate idle time. So it will eventually compensate for this, although possibly not in the time that you need it if it's in the foreground.
And the interesting side effect is that there used to be a lot of JNI code out there that was wrong because the objects were never moving in Dalvik heap. If you're not careful about how you get a pointer to, let's say, a Java byte array, your code will work because we're never going to move that array. Then you move to Art, and suddenly that array might move, and your pointer is pointing to who knows what. And so I think there's the JNI checks are stricter now with Art. So if you write JNI code, or if you're going to write JNI code, be very careful with that. Make sure you test on Art and Dalvik, and follow the JNI conventions in the documentation.
Language does not equal runtime and does not equal hardware. So I gave a different variation of this talk at a conference a month ago, and someone asked a question afterwards along the lines of, so when there's a new release with the JDK, how do you keep up with the changes in the runtime of something? And I realized people didn't quite understand the mental model they needed to about what the language is versus the runtime versus the devices that we're running on. So I thought it would be worth sort of diagramming this for you. So these are all very separate things, right? So we have this Java programming language that we use in Android that has absolutely nothing to do with the runtimes on other platforms. The runtime is a separate thing. Whether it's Dalvik, whether it's Art, whether it's some other runtime on some other system. And then there's the hardware that it's running on. And it's sort of important to understand that this stack is going to look quite different for servers. So traditional Java developers that are writing Java on the back end for servers, writing web apps, whatever, they're going to be in a very different environment than we're in on Android. So they are running over there with some server runtime. It's moving, and it's a compacting collector. It's got huge heaps to deal with, and it deals with them very efficiently with a very different system than we have in either Dalvik or Art. And then you're on the server, and the CPU is really quick. And the memory is essentially unlimited, right? Just huge gobs of memory that you can do oodles of things with. Meanwhile, on Android, which you can tell because it's colored green, we have two different runtimes. We have Dalvik up until KitKat. I think Art was default in KitKat. So what the dynamics you're going to get around the runtime, the performance of the runtime, the optimizations taken, as well as some of the garbage collector stuff we were talking about, depends on which of those runtimes you're running on. And then there's the actual hardware that you're running on.
It's even shaped like a phone.
It is. It's very accurate. I took that from the tool. It's a snapshot from the tool. So we have No compaction, as we were talking about. We do not compact the heap. We can't defragment it on Dalvik. We can do idle time compaction when the app is in the backgrounds with the Arc runtime.
So that is very important because we do compact the heap, but because it's an expensive operation, it happens, like Chet said, when your app is in the background. So that means you can still run out of memory with a ton of free memory in your heap when you're in the foreground. So you still need to be very careful with how you allocate and deallocate objects, because you could run into one of those weird crash reports that you'll get from your favorite analytics reporting tools, and you will not understand how it can run out of memory, and this is partly why. And of course, do not send your application to the background automatically to defragment your heap. That's a bad idea. Basically, any idea you might have based on what we say, like don't do it.
If we were to quantify the CPU for this platform, it would be way slower. And the memory is, in general, between 512 and 2 or more. But it's really important to remember the
technical term
memory.
is not enough.
Not enough, never enough. Also, on the UI threaded, some dynamics here. It's a single-threaded UI system for the most part.
Well, it's a single-threaded UI system, except there's a render thread, and you can have multiple single threads.
OK, so it's a single-threaded, multi-threaded UI system. In general, you are always doing things UI-related, which means input processing, animation, rendering on the UI thread. In general, it's a single UI thread.
Well, little known fact, you can have multiple UI threads in your process. Don't try to do this. It's only framework people who have to worry about it. You can, but don't do it.
We have to test for it, but it's not really a situation that comes up very often.
Yeah.
When we are done with processing all the rendering stuff, then we will send it over to the renderer thread, which will then send it to GL. But you can still think of it as being a single-threaded UI system where all the stuff sort of has to happen serially. And the trick here is to basically eliminate everything that should not or does not have to happen on the UI thread, because you really don't want to stall that. Otherwise, you're going to cross that magical 16 millisecond boundary and jank the UI experience for the
So the best way to make your app go faster is to stop writing code. So just go on vacation, and the best part is you can even justify it.
So in storage, performance varies. So just the raw performance of these storage devices. We've also seen situations where the more that's been allocated into that storage system, the longer it takes to deal with it.
Yeah, if you're interested, you should look up how NAND flash works. It's pretty interesting. So the disk controllers for flash memory are extremely complicated. And turns out that flash memory basically has a garbage collector. And it's very interesting, but the fact is, like, the fuller your storage is, the slower it can get. And things like multiple random writes on the flash can really kill performance. So what happens is that when you have a lot of processes on the system, on Android, for instance, that are writing to memory, to storage memory at the same time, things will really slow down. And we've had pretty bad issues on past devices with that, so it's mostly fixed these days. But so if your app stays in the background, and you're going to do a lot of disk I/O, try to be mindful of the other apps as well, because you writing stuff to the storage might impact the app in the foreground.
That dynamic of storage makes sense. If you just think about this week, Thanksgiving week in particular, as people eat more, they get slower. Storage size varies, so you're not exactly sure what your user is going to have. Is your app going to be able to cope with that flexibility? And the APK size ends up mattering because of these dynamics, right? Are you actually going to be able to fit on the user's device? And will there be noticeable performance problems because it was just too bloated for that particular performance dynamic on their system? In the network, again, this is just like the CPU and memory issues. It turns out your network is probably faster than your users' networks, especially in some locales across the world. They're dealing with incredibly slow networks or data networks that even when they're not that slow, they may cost a lot. So maybe those users are not on those networks as much as possible. A
good way to test, so you can use the emulator. You've seen the presentations before, so there are ways to emulate slower networks. Or if you live in the Bay Area, you could just go take a hike on the hills, by the 280 highway. The network is really bad there. So that's a good way to test and take some fresh air. And again, you can justify it with your boss.
Cheaper too, this is a huge dynamic. Like, are you trying to sell your application into places where they really try to avoid using the data network for whatever reason. But are you very dependent upon that for your application experience? Maybe there are ways that you could write your application such that you can deal with this situation better. Allow them to wait until they're on a Wi-Fi network to deal with that or whatever. And finally, there's a couple of, these are like sort of marketing-ish slogans, but they're really important to keep in mind. One is, every device is a village, right? This isn't just a touchy-feely thing. This is a reality that all of these activities need to live together and services need to live together on the same system to make a reasonable experience for the user. So if your activity is demanding a lot of memory, you're going to kick a lot of other stuff out. So that's great for your activity when it's in the foreground because it got the memory that it wanted. But you know what? When the user leaves your activity and goes back and has to relaunch Launcher because it even kicked that out because you asked for so much, that's probably not a great experience, right? You're not contributing to happiness for the user just because your application was being greedy. And then when you go in the background, when they run anything else, your activity has taken up so much memory that you're probably going to be killed as well. So if all of these things are going to be as greedy as possible in this shared space, then it's just not going to be a happy situation overall.
And there are many ways you can deal with it fairly easily and fairly efficiently. So I'm not going to name the application because I think it's one of ours. But I have a test device. It's a Nexus 9, and I haven't even set up a Google account on it. And every time I boot that device, there's a process running that clearly shouldn't be there because I don't even have an account for that application. So they have a service running. So what you can do in your application, in your manifest, you can disable things like the broadcast receivers, the services, and until the user actually does something in the application that informs you that they want to use the application, they signed in, they logged in or whatever, then you can programmatically enable your service or your broadcast receiver, and the system will remember that. So even across reboots, your service will stay there. And it's really important because that way you will leave the rest of the system free when the user is not that interested in parts of your app.
App Standby tries to address some of this dynamic where if we notice that an application is not actually being used by the user, then we will not allow that application to start using the network or resources because obviously the user has not requested that on the app's behalf. But there's only so much that we can do systematically and automatically in the system. Your application knows better what it needs and what it can disable. And then finally, the first item sort of leads to the second, which is tragedy of commons, where if every application on the device is acting greedily in its own self-interest, then you just end up with a bad experience overall for every one of those applications. Maybe it made sense for you because obviously the most important thing the user could do on their phone is to play your cat video application. But if everybody has the same attitude, then it's going to end up being bad overall. So let's go through some tips. So these are the higher level concepts of why this stuff matters. Now let's go through some of the actual items about it.
And hopefully you have heard of those tips before. So if you feel like we're repeating ourselves, that's a good thing. And we're going to talk about it again until you stop making those mistakes. So no overdraw. How many of you know what overdraw is about? Well, it's getting better every year. Everybody who didn't raise their hand, shame on you, as usual.
Oh, it's because they're busy reading the articles.
I hope. Okay. So if you want to know more, I wrote an extensive piece on the subject. Just Google Android overdraw, you'll find it. Basically, overdraw is when you're replaying the same pixels over and over again. We have tools on your phone that help you catch overdraw, and we have multiple articles that explain how to avoid it. Since KitKat, the rendering pipeline, does some automatic removal of overdraw, it's not perfect. There are things that we cannot guess for you. And when you turn on the overdraw detection tool on the device, it has the side effect of disabling the optimization, so you can actually see where you're overdrawing. And the reasoning is, if you're overdrawing, you're also probably creating too many views, loading bitmaps you might not need, making allocations you don't need. So it's fixing overdraw will also help other parts of your application, like memory pressure, startup time.
Null window backgrounds may seem like a good idea at the time. They tend to.
It was a good idea a long time ago.
They tend to create artifacts on the screen. So if you've ever seen something like when the keyboard comes up, you'll see either garbage or black on the window, in the space where the keyboard is animating over. It's because someone decided to assign a null window background. And this is partly to address the overdraw issue. They said, well, obviously I don't want a background to my window that is then covered with an opaque background of my main container, so I'm just going to remove one of them to get rid of that. And it kind of works in the main, but then there's these specific cases where it causes artifacts. Keyboard animates up, and the window manager doesn't know what to draw there because you told us null. Right? So how do you draw null? You don't do anything. So we don't do anything, and then the GPU will just draw some default error, which is either black or garbage. So there's other situations that can trigger that same artifact. The real way to handle this is to actually have a window background and not have opaque on that main container. So you can still get the benefit of having the background for the window, so the window manager always knows what to draw when it needs to, but then actually use that background as part of the background of your application. Similarly, there's artifacts caused by disabling the starting window. Let's see. So the main reason, there are a few reasons to think about the starting window. One is that you want to give the user immediate response that something has happened. They tap the icon, they're trying to launch your application, which unfortunately is going to take 7 seconds to launch because there's entirely too much happening when you're creating the activity. But in the meantime, we'd like to show them that something is happening so that they don't go and tap it again and wonder what's going on and then uninstall your app. So we quickly launch the starting window. This takes a very small amount of time, usually along the lines of, 200 to 400 milliseconds to bring up this window. We basically peek into the resources, into the theme of the activity, and we say, okay, here's what a window would generally look like for this activity, and we'll pull it up there, and then we'll crossfade it to the activity as soon as it's ready to draw. And this includes, for example, the launch window experience. If you've seen any of the stuff running on M, we're doing the same exact thing. It's just a starting window with a background that happens to have an icon in it. It's very quick for us to figure out what this is, to load it in, and to launch that starting window, and then we're crossfading through the activity as soon as we can. If you disable that starting window, then there's situations where, like the launch experience, where we really should be drawing something for the user, and we cannot because you told us not to. UI stalls, so this relates to the single-threaded, multi-threaded UI thread, the situation that we talked about before. There's lots of things that can cause us to stall in the middle of doing UI processing, so it's good to be wary of these. When you're inflating resources, that's always on the UI thread. So if you're doing a particularly expensive inflation, if you're launching a super expensive activity from another activity, or if you have a deep hierarchy that you're inflating along the way, then that may take enough time that you're going to jank a frame because of that. Handling events. You talk.
There are some places where expensive operations won't be that noticeable. For instance, when you click on a button, but then the places where you want to really be careful. So handling events, like we just talked about. So on-touch event. Then there's the on-measure method that's part of the layout. So you can keep going through the slides.
There we go.
Okay. The on-layout, the on-draw. Keep going, and animations, of course, are going to trigger all those callbacks. So those are really the places where you want to optimize your code, where you want to use systrace, use the profiler, use the GPU profiler if you have to, use tracer for OpenGL, and it's okay, I think, to apply some micro optimizations in those pieces of code because they are so important. Like Chet mentioned, you have 16 milliseconds to do everything you have to do, and turns out that in the land of mobile, 16 milliseconds have a different duration. So depending on how fast your CPU is going, a millisecond might not be the same as the frame before. So 16 milliseconds sometime will be really hard to hit. You might also run into issues, and that's an interesting one, where if you optimize your code too much, we're going to slow down the CPU, so then your code is going to run slower, and then you're not going to be able to go fast enough. That happened to us before. And so the system tries to take that into account, but if you run into that, well, good luck.
Be scrappy, avoid doing too much stuff. Complex view hierarchies, basically the more views you have in there, the more containers, the deeper nested your hierarchy, the more stuff we're doing on your behalf. Traversing it to figure out invalidation, to do measure and layout and all that stuff.
And one of the worst things you can do, and this is probably why we make that the default when you create a new activity in Android Studio, is to use a relative layout at the top of your tree. So if you go, file new layout in Android Studio, just do select all, delete, and start from scratch.
You know why we put it there? It's a test.
Yes. And you all failed it. Relative layout, in a lot of cases, not all of them, will measure the children twice. And so what happens when you measure the children twice is that if some of those children are view groups themselves, like linear layouts or relative layouts, and those cause their own children to be measured twice, then those children have been measured 4 times already. So we have some optimizations in the framework to alleviate that issue, and especially starting with KitKat, the optimizations have gotten a lot better. But you can imagine that if you have 10, 12, or 16 nested layouts, and every one of them measures the children twice, you're going to spend a lot of time doing your measure and your layout. So be careful with relative layout and linear layout. If you use the weight attribute, any child with a weight will be measured twice. So just be careful, measure profile, and try to find a different way of doing your layout if you can.
Please launch your activities fast, present the UI quickly. So that's certainly the purpose of the starting window, but it's also nice if you can present the real content as quickly as possible so the user's not sitting there waiting for your amazing cat video application. Defer extra work. We see a lot of activities or application code that's doing a lot at startup. It has a static block where it's initializing a bunch of stuff that it's going to need eventually. Allocated eventually, right? You don't have to do that at startup and make the user wait every time they launch this thing. Instead, you can wait and do it incrementally as they actually need these things instead.
Yeah, I can give you one example of the way the launcher application at least used to work. I don't know about the current launcher, but back in the old days, loading all the icons from disk, from all the APKs to present a grid of icons was extremely expensive and it would take several seconds. So what Launcher was doing was loading 3 icons at a time, and after loading 3 icons, it would post a message in the UI queue to ask itself to go load the next 3 icons. So if you were fast enough and you opened the grid of icons, you would see them being loaded by batches of like 3 or 6. But that was the idea. So we could start the application itself really quickly, under half a second, but then it would keep building its own UI kind of under the hood. And if you do it right, a lot of it will be off screen anyway, and I'm sure like most of you have never noticed that we are doing that. So in a lot of situations, you can try to use one of those tricks.
Measure cold start. So you want to figure out how long it's taking for your application to launch, and then work on that, optimize it, make sure that it's slow, that it's faster than 7 seconds. But then how do you actually verify that your work has been worth it? If you launch the application and time that thing, and actually I posted something on my blog recently, a couple weeks ago, about ways to do that. Basically, there's a really helpful log now that will just tell you how long this thing took, and then some of the details about that I put on my blog recently. Anyway. Measure that like on launch and see what that number is, and then if you put that in the background and then you launch it from the icon again, that's not the same number. That's called a warm start, right? That activity is already loaded. We're not actually doing much work to bring it up when it's still in memory and still sort of running in the background. So instead, you want to swipe it out. Just bring up recents and swipe it out, and that'll get you mostly to the situation that you get on reboot, which is running for the first time, because that's really what you want to measure. You want to measure bringing in all your code, doing all your static initialization, going through everything that an activity does every time it launches for the first time after boot.
And once again, one of the best tools you can use is systrace. I remember we once identified an issue in the startup time of an application, and the interesting thing that was happening was the application was using a background thread to offload some of the work, to defer some of the work, but at some point the UI thread needed a result from that background thread. So the UI thread was synchronizing on the background thread, but by definition the background thread has a lower priority, so the UI thread was mostly idle, waiting for a lower priority background thread to be done. So be careful with that kind of issue. Use systrace. Systrace will make it very obvious when something like this happens.
So some interaction points to go over. Allow the user to actually get out of immersive mode, otherwise it's a little frustrating. Immersive mode is there for a reason, for full screen video experiences or games, but it's also nice to actually let the users out of the box occasionally. So we've seen this where the starting window, like when applications don't disable the starting window, they don't necessarily do the right thing with it. One of the worst launch experiences I've seen from several applications is typically a game will have like, they want to do their own splash screen that's like tuned to their application thing. So they have their splash screen and then they have their game screen, which is quite a bit different from that. You know, you can sort of see how they're related. But the best of all is they also have the starting window, which has nothing to do with the other ones. So you get a starting window up with some default theme that looks nothing like the rest of the game.
And usually in games, the starting window you get is the gingerbread starting window, which is very sad.
So don't go with the sad window. So they'll bring up this one, then after 3 seconds they'll bring up their own splash screen, then they bring up their own. Much better to actually set the information in the starting window to actually look like the rest of your application, whether it's the status or in the nav bars or just the themes and the style attributes overall. Just make it look like it actually belongs. Or even better, if you want a splash screen experience, just tune the starting window to be that splash screen experience instead.
So essentially, when in your on create, you find yourself changing styling, changing the title, the background of the window, you probably want to do that from the theme instead in your manifest. There are sometimes good reasons to do it in on create because you're computing data, but every time you can do it in XML instead, and you'll get the correct starting window.
Cache your data locally, so don't make it necessary to go back to the server and get that information again. We saw a demonstration of this in Adam and Yeat's talk from yesterday. So if you're going to get that information, you went to a lot of trouble to get it. Wouldn't it be nice if you kept it locally so that if a user goes back to see that information again, we don't have to make another query across it. And also cache the input locally. So if the user has input some information into the system, make sure that you retain that so that if there's something later that depends on that information, we haven't simply lost it along the way. We have exactly 20 seconds to go and about 12 more slides, each of which is going to take 5 minutes.
So the fewer slides we put in our presentations, the longer we talk about each slide. So next time we'll have one slide.
I think we'll call it a day there. Thanks very much. We'll be outside if you have any questions.